Hi, everybody. Thank you for joining us. Today, we want to talk about how you can accelerate LLM fine-tuning and deployment using Domino and NVIDIA Nemo toolkit. My name is Josh Mineroff. I'm a director of solution architecture at Domino, and that means that I get to work with our great partners like NVIDIA to really push the envelope for state-of-the-art solutions that enterprise AI and machine learning teams can use to build different models and get them into production. Now I'll pass off to my co-presenter, Etta Johnson, to introduce herself.
Hi everyone, I'm Etta Johnson. I'm a product architect at NVIDIA. I would like to also welcome everyone to today's exciting webinar. Domino Data Lab and NVIDIA's collaboration has been instrumental in driving innovation and delivering solutions to our clients. I'm delighted to partner with Josh today for this exciting webinar, and let's get to it.
So what we want to talk about today is a specific use case to build a clinical decision support model. We're going to go through kind of a sequence of steps. First, we'll give you some background on what exactly that use case is about and why it's important. We'll talk about how you can start by using a base model and do that quickly to get something off the ground and get from 0 to 1. Then we'll talk about reasons that you may want to self-host that model and how you can go about doing that. And we'll move on to fine-tuning and deployment, and then how Domino and NVIDIA can additionally help get those models into production to make them more scalable and governable. And then at the end, we'll have some time for Q&A. And as we go through this, if you have any questions, feel free to put those in the chat. We'll get to as many of those during the talk as we can, but if not, we'll be able to address them at the end during the Q&A session. So I want to start by giving you a really high-level view of Domino. Domino is the enterprise platform for AI that companies can use starting from developing models, getting them all the way into deployment, and then monitoring those models once they're actually out in the wild to make sure they're still performing as expected and delivering value to the organization. The way that we do that is we provide data science teams with on-demand infrastructure, so you get self-serve access to the compute and tools that you want to use. We make it really easy to collaborate and reproduce other people's work. We speed the process of getting a model through development into production. And then we do this all in a way that's safe to scale across the enterprise. So it's easy to manage by IT. You can put cost controls in there, and you can also see how these models are performing to mitigate risks to your organization. And of course, you can get all these benefits using NVIDIA products and services because Domino is certified for use with NVIDIA AI Enterprise. And now I'll let Etta expand a little bit more on what that means.
Thanks, Josh. NVIDIA Enterprise AI Platform provides an end-to-end full-stack solution with enterprise-level reliability and security for AI productionalization. At a high level, let's go over each layer. On top of the NVIDIA accelerated hardware infrastructure built on the cloud, your own data center, edge or embedded platform, and infrastructure optimization layer with cloud-native management and orchestration capabilities provide secure and scalable optimizations. On top of those, the next layer encompasses AI and data science development and deployment layer with best-in-class AI software. This reduces open source development complexity. This is where Domino Data Lab plays a huge role for enterprise customers, providing workbench and ML ops capabilities, specifically around reproducibility, knowledge management, governance, and FinOps. Domino is also certified for NVIDIA AI Enterprise. On top of this layer, NVIDIA Enterprise AI Platform provides AI workflows, frameworks, as well as pre-trained models designed for specific AI enterprise use cases to achieve business outcomes, providing a faster time to value. Some examples include intelligent virtual assistants for customer call centers, drug discovery pipelines in healthcare and life sciences, and digital fingerprinting for detection of cybersecurity threats. In today's webinar, we will walk you through a healthcare decision support system for evidence-based decision-making for physicians. Our problem statement here is basically some portion of negative outcomes in a healthcare facility are preventable or caused by suboptimal treatment plans. For example, according to research, up to 65% of inpatients are exposed to known potentially harmful combinations. And again, according to research, up to 84% of clinicians identified lack of awareness as a barrier to adoption of best practice guidelines. With that, we're going to implement a decision support system using LLMs to assist doctors in evidence-based decision making. So some of the business outcomes we're targeting are improved patient outcomes, enhancing treatment plans with up-to-date research findings, ensuring uniform and rapid access to the latest medical knowledge, and finally, overcoming the challenge of staying current with the vast amount of new medical research data. With that, we will demonstrate how we fine-tune a base model using PubMed QA dataset. This is a specialized dataset that focuses on answering biomedical research questions using PubMed articles to answer clinical questions. For this, we created test, trained, and validation datasets before our session. So if you would like to create these after the webinar, please follow the instructions in the PubMed QA GitHub location. Before we delve into the demo, let's go over the steps of creating a decision support system using LLMs. The first decision is choosing an LLM. With a plethora of options today, given the increasing number of available models and their diverse capabilities, it is essential to consider the specific requirements for your own use case, particularly around domain relevance, ethical considerations, and accuracy requirements. When it comes to selecting a foundational model, there are several considerations based on your use case and your desired deployment pattern. The two key GenAI deployment patterns we have been seeing this year are leveraging managed generative AI services and do-it-yourself option. There are certainly trade-offs when it comes to choosing which option to go with, but with the managed GenAI services option, typically, which was a lot popular earlier this year, the main benefits are ease of use and a faster path to production. Some trade-offs, on the other hand, include being limited to offerings by a certain provider, and of course sharing of enterprise prompts and data externally using external API. Another drawback is that you have limited control over your GenAI strategy for aligning with the latest innovations in the ecosystem, as you're tied to a single managed provider strategies. Many organizations today are leaning toward the second option, which is the do-it-yourself deployment. To keep their data secure and private, enterprises deploy LLMs in a self-hosted environment across their data centers, whether it's on-prem or cloud or hybrid. The challenge with this option is that enterprises need to optimize for performance for their own infrastructure themselves. They also need to create and maintain custom code for APIs, pre-process inputs, post-process outputs, and fine-tune LLMs. NVIDIA is taking the best of both worlds approach with NVIDIA NIM and provide an easy and free path to try a combination of state-of-the-art enterprise-ready NVIDIA models like Nemotron 4340B model and performance-optimized community models like Llama 3.1 model family at ai.nvidia.com. We also provide a hosted API or a self-hosted API option. To use either the managed or self-hosting option, all you need to do is to generate an API key using your free NVIDIA Developer Program subscription or your Enterprise AI subscription. Let's take a quick look at build.nvidia.com. You see several models available in different domains on this page for you to try. And we will mainly focus on the LLM models under reasoning domain today. So basically, let's click on one of these, which is one of the chat models, Llama 3.1 405B instruct model. And let's click on that. As you can see, there's a playground for you to interact with this model and ask questions. And we get a pretty fast latency as a response. And when you're ready to programmatically interact with this service, you can use one of the code snippets on the right side. We have a Python, LangChain, Node, and Shell code snippets that you can copy and paste to your Domino notebook. And before you execute the code, you will need to generate an API key, as I mentioned before. And once you're ready to switch over to a deployment in your own premises, there is the Docker option where you can log into the NGC Docker repository and pull NIM containers and execute and stand up the NIM service in one Docker command. After that, you can interact with this service in your own environment using curl command. With that, I'm gonna turn it over to Josh for AI Gateway.
Thanks, Etta. I want to talk a little bit about how we can use all of these models that NVIDIA puts together and packages up for us, and also get a lot of the benefits of Domino on top of that in terms of governance, making it really easy to collaborate and also kind of track utilization. The way that we do this in Domino is with AI Gateway. And I'll show you a demo of this in a second, but just a few high-level things to keep in mind as we go through here. Some of the benefits that AI Gateway gives you is it gives you a way to control user access to different LLMs. So you kind of put the credentials in when you configure AI Gateway, and a user consuming one of those models doesn't have to necessarily know how to access the upstream model. So you don't have to worry about them taking that access outside of Domino or into an environment where you don't want to run that. It also gives you consistent access to a variety of LLMs, so users can easily switch executions to use a different model if they want to, and it's basically all the same code. And we also log the activity that happens for each of these LLMs from a governance perspective, so you can understand how they're being used or exactly what kind of data is being sent to them. So we'll start here. We'll pick up where Etta showed us in build.nvidia.com. And again, we're looking at Llama 3.1. So remember, our goal is to train a clinical decision support model here to help clinicians answer questions around maybe what kind of treatments to use on a patient or what kind of medication to prescribe. So I already have a Llama 3 model set up in Domino, but since this is a new project, it would be nice to use a newer base model. So we're going to use Llama 3.1 here. On the side, in the sidebar, you can see some of the information that we're going to need when I switch over to the Domino UI. You can see kind of the base URL that's going to actually allow us to hit this model hosted by NVIDIA. You can see the model name, and you can also see that an API key is referenced here, and I already have my own API key. So now we're going over to the Domino UI, where we can see all of the LLMs we have configured already with AI Gateway. So I, in my deployment, have a lot configured, and the process for creating one of those is I'll go here. I can give that endpoint name. So I can choose the provider here, and when we're running it with a NIM, we're going to use OpenAI compatible because it's an OpenAI compatible endpoint. I'm going to choose that it's a chat type endpoint. I'm going to use this model name that we pull directly from build.nvidia. And then I'll put an API key in here, and I'll use that same base URL that we had. On top of that, you'll notice that Domino allows us to inherit some of the RBAC that's baked into the platform to say that certain users can interact with this. So I can make this available to anybody that has access through Domino, or I can limit it to specific users and organizations in Domino. And then I would save this endpoint, and it will actually be created. So I've already done that here with this remote NIM. And this shows me some of the code that I would need to do inside of a Python environment to interact with this. And I already have actually a workspace running inside of Domino, which is our way of running interactive notebooks. And you can see on the side here, this is a list of all of the AI Gateway endpoints that I personally have access to. For each of these, I could copy any of the code needed to connect with that and put that in here. That's actually exactly what I've done here. I've just added a little more formatting to the output, and then using this prompt that's representative of the type of questions in the PubMed dataset, I can actually interact directly with the remote NIM, and this is hitting through an API the exact same experience as if I typed into this chatbot here. But now I can bake this into an application or a proof of concept for prototyping. So it's what I want you to take away here is it's really easy to get started using a foundation model. And we want to actually, in this case, try to do even better than just a base model. So the traditional approach to that, right, would be kind of full fine tuning of the model or maybe RAG, and we'll talk through some options of what you could do to improve performance there. So there are a couple different ways that you can customize LLMs to your needs. One that many of you may be really familiar with is prompt engineering. So this is giving some general context to the model along with your actual prompt to give it some idea of what type of output you would like or what context you want it to keep in mind as it goes through whatever you're asking it to evaluate. RAG is another method. And in this case, we're using outside information, usually from a vector database, and making that available to the model when you actually submit a prompt. So you have your prompt, you pull a bunch of supporting documentation and information and submit that as part of your prompt. So now it has additional context, maybe related to the specific medical field in this case, or something about your business that it may not have had otherwise. Full fine-tuning is the classic way to kind of improve the actual model. So what you're doing here is you're just doing additional training on top of what's already been done with the base model, but you're maybe only unfreezing a small part of the model to work with, or you're training the entire model and doing that with a data set that's specific to the use case that you want. That should improve the performance in that specific use case. But the downside here is it can be really expensive, right? You have to go through definitely an abbreviated version, but still something relatively close to the type of training that the model went through in the first place to be created. Parameter efficient fine-tuning is actually a really great way to get most or all of the benefits of full fine-tuning, but with a substantially smaller computation cost and time associated with it. And there's a couple of different ways to do this that we'll talk through in a bit. But in order to do any kind of fine-tuning, we actually have to be able to run the full model locally. And so far, we've been talking about running this through build.nvidia.com. We're doing it kind of remotely through the web or an API. So now I'll pass it over to Etta to talk through how NIMs also allow you to deploy on-prem, and that's going to let us do some of this fine-tuning.
Let's now talk about inference microservices with NIM. As enterprises transition from GenAI experimentation to deploying and scaling AI applications in production, the primary focus is model deployment and inference. NIM provides containers used to self-host GPU-accelerated microservices for pre-trained and customized AI models across clouds, data centers, and workstations. NVIDIA offers NVIDIA NIM microservices to seamlessly abstract away the complexities of AI model deployment and packaging for production. NIMs leverage pre-built containers and Helms under the hood. With one-click deployment, NIM microservices provide performance, security, and the desired level of control. Llama 3 NIM, for example, provide up to 5 times the throughput compared to deployment of Llama 3 on the same hardware. Supporting a wide range of AI models, including open source community models and NVIDIA AI Foundation models, NIM ensures secure and scalable AI inferencing on premises in the cloud with secure industry standard APIs. For example, for the LLM NIMs, they conform to the open AI APIs. Built on robust inference engines like TensorRT, TensorRT LLM, and Triton, NIM is the fastest and easiest way to achieve AI inference at scale. NIM as a pre-built container for each model also provides standard observability data feeds. We also support built-in support for auto-scaling with Kubernetes on NVIDIA GPUs. NIM microservices are part of the NVIDIA AI Enterprise that provide enterprise-grade qualities for security patching, validation, and quality assurance with enterprise support. And they're designed to lower total cost of ownership with the best latency and throughput running on any NVIDIA accelerated infrastructure. So how do they work under the hood? NIMs are essentially containers that bundle a model, such as Meta Llama 3.1 8B instruct model that we see on the screen, with a runtime that works on any NVIDIA GPU with enough memory. Some models and GPUs are specially optimized for better performance. NIMs get the models from NGC, which is a repository of GPU-ready software for AI and high-performance computing. NIMs can also use a local cache to save time and bandwidth. When a NIM runs for the first time, it detects your hardware and a model registry to find the best model version for your system. For a set of NVIDIA GPUs like A100, H100, and L40S, NIM uses TRT LLM library for inference with an optimized TRT engine. For other NVIDIA GPUs, NIM downloads a non-optimized version of the model and runs it using vLLM, which is an open source inference framework. The user can run a single command to launch the LLM NIM without having to worry about the details of the hardware, software, and optimization. NIMs also share a common base, so downloading more than one NIM is very fast. Here's an illustration of how a Llama 3 70 billion instruct model or NIM microservice run optimized models for different combinations of detected hardware, number of GPUs, optimization profiles, whether it's throughput or latency, and precision behind the scenes. NVIDIA NIM automatically explores the complex combinations of these optimizations that we see on the screen, then pick the optimal configuration or optimization profile depending on the objective, which could be latency, throughput, or balance in your use case. We do this for you, so you don't have to implement sweeping scripts or spend people or compute resources to do these steps yourselves. Also, NIM provides model-specific optimizations out of the box. So here's an example of how having NIM on improves the throughput 2.5 times compared to NIM off in a sample translation task when using Llama 3.1 8B model. On the right side, we're also seeing the world-class response times with Llama 3.1 405 billion model, which is a very large model using TensorRT LLM. In this case, we're using 8 H200 GPUs for long content summarization and RAG chatbot tasks. We looked at how easily we can use these NIMs and deploy them using Docker. Once you're ready to productionalizing NIM in your own environment and self-host these models, the next step is to pull these NIMs from your NGC catalog. Let's take a quick look at NGC catalog. And as you can see under Helm charts, you can simply search for NIM, and you can access the Helm charts to install NIMs. We currently have 2 versions of the Helm chart. And for a particular NIM, you can essentially install this Helm chart in your own Kubernetes environment. We also have the source code of this Helm chart in our open source GitHub repository in github.com NVIDIA NIM deploy git repo. And we provide the source code of this Helm chart. And please note that the source code for Helm charts in this open source GitHub repository is mainly for experimental purposes. And for production deployments, please use the Helm charts from the NGC repo. When I click on the Helm directory, in the README, you're going to find step-by-step instructions on how to deploy this NIM in your own Kubernetes environment. We start with defining our NGC API key and creating a couple of secrets in our Kubernetes cluster. In this NIM deploy repository, you'll also find example implementations of NIM using kserve and a NIM operator that is currently in development. You will also find under Cloud Service Providers section how to deploy NIM Helm chart in AWS, Azure, or GCP, or NVIDIA NVCF, and sample implementations. Today, we're going to mainly focus on AWS EKS implementation, and we can quickly go over the README file in this directory, where you can see step-by-step instructions on how to deploy an AWS EKS cluster using CloudFormation templates, and then deploy the NIM Helm chart in your EKS cluster. Prior to this session, I already created my AWS EKS cluster and created these secrets. So let's switch over to my VS Code and take a look. Here are some of the secrets that I already created in my AWS EKS cluster. And let's look at some of the pods that are already running. I currently have Prometheus pods running in this EKS cluster. And as a next step, I'm going to show you how I simply deploy the NIM Helm chart. So let's go ahead and I copied this command from the GitHub repository. Let's go ahead and install this NIM using the single command for Llama 3.1 8B instruct model. This will take a couple of minutes, so in the meantime, I'm going to show you how this custom values YAML looks like. So before we look at the custom values YAML file, I want to also mention that my EKS cluster, the CloudFormation template I used for this cluster stack, has a couple of G512 X large instances, which gives me essentially like 8 A10Gs. With that, you can use different storage classes, including EBS or EFS. I chose to use the EBS in this example. In my custom values YAML file, I'm specifying the NIM for the Llama 3.1 8B instruct, and also the model location, where I can pull the model from NGC using my secrets. In the persistent configuration, you see the EBS storage class defined. And also, like as you can see, I can define my how many GPUs I would like to use for this pod deployment, and I specify 2 810Gs for Llama 3.1 8B instruct NIM. Here's my service definition and some also like configuration around Prometheus metrics and autoscaling. As a next step, I can choose to create port forwarding for these pods, or I can choose to create an egress, which I'm going to be doing here using my ingress YAML sample from the GitHub repository that I cloned. I already created that, so it's already up. Now, let's check if my NIM pod is up and running in my default namespace. And here it is, it's ready for me to consume. Let's take a look at a couple of test commands. First, I'm gonna define my elastic load balancer DNS that I specified in my ingress YAML. And this is the DNS that I'll be using. And here's an example curl command to send a request to this NIM that is deployed in my Kubernetes cluster. Here's the result. Now I'm going to turn it over to Josh for parameter efficient fine-tuning.
So now that we have the model running locally, and in this case, actually, Domino is a Kubernetes native application, so we're able to deploy the NIM even directly into the same underlying Kubernetes infrastructure as where Domino is running. So from an IT perspective, they don't have to maintain any additional hardware, and then you just put it in a different namespace, and you can still interact with it from Domino. And we'll talk through that a little bit later in the next demo. So there are a couple different ways that you could do fine-tuning with parameter efficient fine-tuning. And remember, that was the reason that we wanted to bring this model on-prem. So first, you could do prompt tuning. What this does is instead of kind of traditional prompt engineering, where it's like a human readable format, in prompt tuning, you're directly training an embedding that kind of represents all of that prompt engineering, and that gets added to the prompt. So it's not necessarily going to be human readable, but you can optimize it even further and maybe get better performance than you can get with traditional prompt engineering. Prefix tuning is like prompt tuning, but instead of just adding an embedding to the input prompt, it actually gets added at different layers throughout the model. P-tuning is kind of the next step of this, where instead of having a static set of embeddings that get added at each layer, you use another model based on the prompt to determine which embeddings you should add to the prompt. And what we're going to use today is LoRA. And LoRA stands for low rank adaptation. And what this allows you to do is kind of the traditional fine-tuning process where we're taking the entire matrix of weights for the model, and we're decomposing that into two smaller matrices and training those. And that has a lot of benefits that we'll talk through. So I want to dive a little bit deeper into how LoRA works. A lot of us are, maybe don't have advanced degrees in math, so looking at this doesn't intuitively make sense. But I do think all of us can walk away completely understanding how LoRA works, kind of what the benefits are and why it works. So we'll start by looking at traditional fine-tuning. So here you can see on the left, we have an existing foundation model. In this case, that's going to be the Llama 3.1 8 billion parameter instruct model that we pulled down in the NIM. This has some set of pre-trained weights. So that's using a specific input. It's going to give you an output embedding. And in traditional fine-tuning, what you would do is you use backpropagation. You get the change in weights that you want. You add that back into the pre-trained weights. And over time, the pre-trained weights turn into the fine-tuned weights. And now you have your new model. And you're doing this process with task-specific data on the bottom. So this is why it gets better at the specific use case that you're training the model for. The main difference with LoRA is we actually don't combine this change in weights back with the original pre-trained model weights. We're going to keep them separate through the entire process. And the reason that's beneficial is actually the change in weights can be really heavily reduced. So it's low rank. And what that means is that you sort of don't need all of the numbers in the matrix to be able to rebuild the matrix. Like a lot of rows or columns in the matrix are going to be redundant. And since that number tends to be relatively high in a fine-tuning weight matrix, we could take advantage of that to get two substantially smaller matrices that make the process more computationally efficient. Here you could see if the set of weights is an m by n matrix, we can multiply two smaller matrices, and an m by r and an r by n matrix multiplied together will give you another m by n matrix out. But the actual sum of parameters in matrix A and matrix B is substantially smaller than the amount of parameters in delta W. And that difference becomes even larger the smaller that R gets, right? So if you have just a column for A and a row for B, it's M plus N instead of M times N. And going back to the original figure, that's exactly what this is showing. So this is showing, right, that you have still that set of inputs, X, you have the H, which is the resulting embedding of this fine-tuned model with LoRA. You have the original pre-trained weights, which we haven't touched. And A and B being different size matrices than W is just represented here by them being trapezoids. And you can see that the smaller that R is, kind of the smaller the sum total of parameters in A and B is going to be, and the more we get to benefit from the computational advantages of LoRA. So let's say if you have a 10 billion parameter model, and then it's a square weight matrix, right? So you have 100,000 parameters in one direction, 100,000 parameters in the other direction. If we instead use LoRA to fine tune that, we don't have to tune 10 billion parameters. And based on what R is, and in a lot of cases, R can be 2 or 4 or 5. And in the case of 2, we end up updating 10,000 times 2 and 10,000 by 2. So it's actually only 400,000 parameters that we have to train instead of 10 billion parameters. And the way you would approach this usually is that R will be a hyperparameter as you go through this process, and you can choose sort of based on the types of performance or efficiency that you want in your training, what R makes sense compared to a given type of accuracy or value you get out. So now we're going to go into a demo of how you can use Nemo in Domino to actually train a LoRA on top of a model that we pulled out of a NIM, like in this case, Llama 3.1 8B. So I'm going to switch over into the Domino UI. Right now, I'm inside of a project that we've created. This is for the PubMed QA parameter efficient fine tuning. Inside a project of Domino, this is like the core unit of work in Domino. So you can think of it like a Git repo, but there's also a lot of other things included in a project. So here we have a bunch of different code. We have some notebooks, including one that Etta is going to go through. We, in this case, to get the model ready, use the Git repository, and that's also tracked inside of the project. We have some different data that's available here. So we have what we call in Domino a data set, and this is effectively a mount point that can be backed by NFS or EFS or whatever kind of shared file system solution you have available with the infrastructure that Domino is configured in. And here we have a few that are relevant. So we have a data set with the base models. So this is where we've already pulled the Llama 3.1 8B instruct model. So we don't have to wait for that to pull every time. If you start up any execution, right, it's going to be able to mount directly this data set at this path inside of Domino and be kind of immediately available. You don't have to wait for 58 gigabytes to pull down. We also pulled in advance the PubMed QA data set. And that's going to show up at a path inside of our notebook or workspace. In this case, the data set is relatively small, but we have customers that we work with that will pull down multi-terabyte data sets, and being able to immediately mount those and not wait for those to pull every time you start a new execution is hugely valuable for your time between iterations to train a model or do different projects. And finally, since we have the hosted NIM running in the same infrastructure as Domino, we also have what we call in Domino external volumes. These are volumes that are not managed by Domino. So data sets are managed by Domino on some external file system, but external volumes allow you to add any kind of file storage and make Domino aware of it. So what we've done here is that NIM is aware of this volume, and it knows this is where to expect LoRA adapters. Domino is also aware of the volume, so when we run a notebook or an execution, we're going to see at this path a folder that if we put the models in the correct folder structure, that the NIM running in Kubernetes is going to be able to have access to that, and it's going to be able to use any of the LoRA adapters that we place in there. So for any type of like execution or work that we do in Domino, we have interactive and non-interactive ways to work in Domino. And when working with a notebook, you would do that in what we call a workspace, which is an interactive session. So the way that you would do something like this in Domino, we already have a lot of these prerequisites set up. So being certified with AI Enterprise, we have a really great experience to pull images from NGC. Here we're using this Nemo framework image, version 24.07. And we've already pulled that from NGC. Domino's managed that process for us. And has done that in a way that's made sure it's going to be compatible with Domino. We're going to have access to an IDE in there. We also have hardware configured, and we can pick this hardware from a dropdown. So here, right, we could just use a GPU job, but if we, like Etta had mentioned, right, different models are going to require different amounts of GPU memory. So you could pick a larger type of hardware tier or even a non-GPU hardware tier if you need, depending on your use case. Domino lets you spin up distributed clusters for larger scale training, which we're not going to touch on today. And then finally, we can see that Domino is telling us that these, like the external volume that we want with the LoRA adapters is going to be available. And it's also going to have these data sets available, and they're going to be mounted and available to us from inside the notebook for us to work with. So now I'll launch this, and then we'll switch over to Edit or walk through the notebook.
Thanks, Josh. Now I would like to show you a demo notebook in Domino, where we took the Llama 3.1 8B instruct model and created LoRa adapters using parameter-efficient fine-tuning with Nemo framework. We use Nemo container 24.07 version in this demo. And so we ran this notebook prior to this session, as the training step takes around 15 minutes with a single A100 GPU. But I'm going to go over like each cell and explain what we have done. So you can also find this notebook in the resources section of this webinar. First, we need to make sure that we download the Llama 3.1 8B instruct model in the Nemo format from the NGC. So we did that. And in step one, actually before step one, let me go over the 4 steps that we followed. We prepared the data set using the instructions in the PubMed QA GitHub location. Then we run the PEFT fine-tuning script using Nemo command line scripts. Then we did an inference with a Nemo framework using our test data. And then we checked the model accuracy, comparing the predictions in the test data with the ground truth. So in step one, we prepared a data set using the code in the PubMed QA GitHub location. Let's take a quick look at one record. As you can see, there's a question field, context field, and a couple of yes and no fields, and a long answer field. After we executed this cell, we created a train, test, and validation data sets in JSON-L format and saved them into some mount points in Domino. In step 2, we actually run the PEFT fine-tuning job using LoRA technique using Nemo framework. In this one cell, we essentially use the CLI command for Nemo parameter efficient fine-tuning, which is essentially a Python script in the container that we pulled into Domino prior to this session. And we defined a couple of hyperparameter options, configuration options, that we use for our fine-tuning. So we essentially specified the model location, the Nemo format model we downloaded from NGC, as well as the 3 data sets for train, validation, and test. We also specify our scheme, which is the parameter efficient fine-tuning technique we're going to be using for this training, which is LoRA. And we also specify the output directory where Nemo creates the LoRa adapter and checkpoint files. A couple of things to mention here. In this case, we're using only one A100 GPU, so we set the parallelism, tensor parallelism, and pipeline parallelism configuration options to 1. These are 2 major model parallelism techniques that you can use. But if you're using multiple GPUs in your production environment, it's good to set these greater than 1. And as a reminder, tensor parallelism essentially is a technique that splits individual network layers across multiple GPUs to minimize latency in a single node. And pipeline parallelism helps you split contiguous sets of network layers across multiple GPUs with a goal to maximize GPU utilization in a single node. So this cell runs around 15 minutes. So I'm gonna quickly scroll to the next step. After the training is complete, essentially Nemo framework creates a couple of files in the output directory we specified in the previous cell. Here you go, we print the checkpoints as well as the LoRA adapter, which is in Nemo format as well, for the fine-tuned model with the PubMed QA dataset. In the next cell, after verifying the checkpoints and the model LoRA adapter file, we create batch predictions for our test dataset. This is again one single command with Nemo framework. We're using one of the Python scripts to create a JSON-L file with our predictions. After we run this command, I'm gonna skip over to step 4. We check the model accuracy. And to do that, we use the generated file and we evaluate the accuracy of the predictions with the test data set against the ground truth. And for this, the PubMed QA dataset provides a nice evaluation PY Python script, so we can simply use that to compare the results. And the expected accuracy and F1 score are 0.79 and 0.59 respectively, and we achieved a 0.79 and 0.55 accuracy, which is very close to what we expect to get. After that, we simply copy the LoRA adapter that is created as part of the fine-tuning job to another mount point in Domino, so we can create a NIM for inference. At this point, I'm going to hand it over to Josh again, so he can show us how we can use this NIM for inference.
Thanks, Etta. So now that we have this LoRA adapter trained and in that external data volume where it's going to be available to the NIM hosted in Domino, we're going to be able to actually configure a new AI gateway endpoint to reach out to the NIM, but to let it know that that's the model that we want to use. So I'm going to show kind of two things here. So first, I want to show kind of the difference between, originally I had showed you how to set up a remote NIM in AI Gateway. And if we look at that, right, we can see sort of OpenAI compatible. We use chat, we put the name of the model, and the AI or the API base here is this remote integrate.api.nvidia endpoint. When we pulled the NIM into the Kubernetes cluster where Domino was, we're able to create a very similar endpoint. You can see it has even the same model name. They're both OpenAI compatible, and they're both using the chat type. But now, instead of that remote endpoint, we're actually using an endpoint that is local inside of the Kubernetes cluster that we're in. So if you're familiar with Kubernetes, this format may look familiar to you, but if not, it's basically saying that we're inside of the cluster. We're using a service in the NIM namespace, and this is the specific endpoint that we're connecting to. So just by changing basically this, and the API key is not actually relevant when you run it on-prem like this, we're able to, using the same exact connection, now reference the NIM running on-prem instead of the running in the web. And similarly, we're able to take advantage of the PubMed QA LoRA adapter. So here we're connecting to actually the same exact API base as we were before. One really cool benefit of LoRA over other methods of fine-tuning is because we keep the weights separate the entire time, this gives us kind of a pre-packaged delta W that we can use. So we can keep one copy of the Llama 3.1 8 billion parameter model loaded in the GPU and kind of ready to serve. And then we can pull in different LoRA adapters and really efficiently use the same inference hardware to serve a bunch of different models without having to load different 20 or 30 gigabyte models. So I've actually pre-created these already, and I'll show you really quick that inside of a Domino notebook, The exact same experience as what we had before is true, right? So in the past we had, or in the past demo we showed with this like remote dash NIM. Now I'm using kind of the new version that's hosted directly here. And when I run that, it's going to give me a result in the same kind of format with the same usability. So it makes it really easy for a consumer in Domino to interact with any of these LLMs that you have running as a NIM or a LoRA adapter on top of those. And to change to that new endpoint, all that I have to do is add this dash PubMed QA. That's what I named this endpoint. And when I run this similarly, Red is also going to give me an output here. And something to note actually is that as a consumer of this, because all of this inference is running, it's local in the cluster, but it's not necessarily inside of my execution. Each consumer of a NIM in Domino doesn't necessarily need to run on a GPU, right? A job can run on whatever type of hardware is required and sort of outsource that inference to the backend NIM service. So far in these demos, we've talked about a couple of different functionalities and features of Domino. We talked about AI Gateway. We've sort of talked about under the hood how you can manage data access and hardware. There are a bunch of other functionalities of Domino that we didn't have time to talk about today. We have anything from AI Hub, which is templates that kind of are quick starts for you to start building as soon as possible for common AI use cases and things like RAG. These give you the software that you need, any additional configuration details, and that gets packaged up from Domino so you can start a project and not have to build the entire project from scratch. You can start from kind of a best practices starting point and build on top of that for your specific use case. We also provide federated access to vector data sources, right? We talked a little bit about RAG, and you can manage those connections through Domino. That's all kind of on the Gen AI level. Domino also has been working with leading machine learning and AI enterprise teams for almost a decade now. So we also have a bunch of other more broad enterprise functionality for things like FinOps to help you monitor and reduce costs associated to model training and AI. We have Model Sentry, which allows you to have model review processes. So you need approvals maybe from the appropriate people, or you want to confirm that specific tests or validation have been done before a model goes into production. And we also support hybrid and cloud compute workloads. So from that same dropdown that I showed where you could pick GPUs or smaller hardware, you can also pick similar hardware, but in completely different areas, right? So that may be, in this case, we ran in AWS, but you could also run in Azure or GCP or an on-prem DGX cluster. And this sort of supports you through the entire life cycle of building a model, actually getting that out into production, and then monitoring the model once it's out so you know when to improve and you can get kind of faster and more collaborative through that entire process. And the way that we do this is by being a system of record for the entire data science and AI lifecycle in your organization. We allow you to bring in any of the tools and data that you want to use, any language or compute framework, and Domino runs on top of Kubernetes. So like I said earlier, we support sort of any infrastructure with CNCF compliant Kubernetes. You can connect to your different data platforms. You can develop models inside of Domino collaboratively and track them through their whole life cycle, and then get them out as publishable artifacts that can drive value for the business. So these can be things like APIs. They can be web apps. You can also package them up in a container and deploy them somewhere to the edge. And all of this can be orchestrated from a single pane of glass through Domino and let you leverage sort of the best in breed tools in really specific areas as those become more important to your organization or your specific needs grow over time.
Next, I would like to also go over the end-to-end platform capabilities built on top of Nemo microservices. This is extremely important if you're operating in an air-gapped environment or you want to have full control over the lifecycle of an LLM workflow, from data creation to model fine-tuning, including RAG to evaluation within your clusters. Nemo microservices include a lot of microservices, and we're constantly working on new ones, but here's a sample of the ones that I would like to mention today. Starting with Nemo Curator. Nemo Curator is designed for fast and scalable dataset preparation and curation, and it leverages GPUs with Dask and Rapids under the hood. This results in significant time and cost savings compared to traditional data engineering techniques. NVIDIA Nemo Customizer, on the other hand, enables fine-tuning of LLMs from personal data using your own enterprise data in your own environment using open source models. Nemo Evaluator enables evaluating custom models across academic and custom benchmarks, also LLM as a judge, among other features through simple APIs. Next, Nemo Retriever is a collection of microservices that enable RAG in your environment. Nemo Retriever comes with multiple NIMs for embedding and re-ranking, and it has seamless integrations with vector databases to implement RAG. And last, we talked about NVIDIA NIM extensively in today's webinar. It provides state-of-the-art large language models, and so you can essentially stand up your services in your own environment. And NIMs also seamlessly integrate with other Nemo microservices as well.
All right. Well, thank you everybody again for attending this session. If you want to learn more about what we talked about today, you can go to either of these websites. You can go to domino.ai/NVIDIA and learn more about Domino and also our partnership with NVIDIA. You can go to NVIDIA.ai to learn more about Nemo and some of the models and other products that are available for you to work with things like this. And then also I implore you, if you really would like to see in more depth kind of some of these use cases and other applications you could do in Domino, that you join one of our live weekly demos. The next one is actually going to be next Thursday on September 5th. And you can check it out at this URL, domino.ai/weekly demo, and we'll stick that in the chat. Now we do have a little bit of time for Q&A. So if you have any other questions that you weren't able to post during the talk, please send those now and we'll be able to respond to them. Thanks again.